We need to add some component data. So before we can write a system, we need to add some data to this component. I'm sorry, we need to add some components or AKA data to this entity so that we know what it is. So I'm going to go into our code. Actually, well, before we do that, let's create a script here, create a folder. I'm going to set up a couple script folders because we're going to bifurcate and just kind of group a couple things together. We're going to have some behaviors. We will still have mono behaviors. Just because we're writing a pure ECS system doesn't mean we can't use mono behaviors, doesn't mean we shouldn't use mono behaviors. We still have them, we can still use them. We're going to have components, right? These are going to be all of our data bags, all of our objects that just contain data. We're going to have systems. And I think that's it. I think that's all we need. So from a component, let's go ahead and create a new C# script. And I'm going to call it a player tag. And now we're going to open up our editor here just so we can get it in. And once it opens up, I'm actually going to delete all of this. We're going to delete all this. I'm going to rewrite it because a component in an entity component system is not a class. It is a structure. So we're going to create a public struct, and I'm going to call it a player tag. And it needs to actually inherit. I know we talked about object-oriented programming and inheritance systems and things like that, but this struct does need to inherit from something. This is how Unity knows that this is a component for the ECS system. So you need to inherit from iComponent data. It has nothing, it's just an interface. It doesn't have any methods you need to implement, which is fine. And then the other thing we want to add is a generate authoring component. This is a tag, this is a attribute that we want to add to our structure. This tells the editor that even though I'm not creating a mono behavior, this is not a mono behavior, I want this component data to look like a mono behavior in the editor so that I can add it to a game object that is going to be converted, so that when it's converted, this component will be added to it. It's basically a way to bind in entities and components into the editor that really only knows about game objects and mono behaviors. So it's a little bit of glue. I'm not going to add any data. So, and this is why I call it a player tag. There are component data in an entity component system. You have components. Components don't actually need to have data. It can be an empty component. And you can then use that as a search system. So you can have entities that contain this player tag, and then we can find all entities that have the player tag. And just for that, we don't want the data from the player tag. We just want to use the player tag component as kind of a tag, as kind of a search query. So that's why I'm not going to add any data to this. I'm going to do a input system. Now, normally how we would do an input system, or how you would probably do an input system, is you just have a mono behavior, and in an on update method or a fixed update method, you're seeing, hey, is mouse button down? And if it is, execute an action. I don't want to do that for this game, and there's a couple reasons I'm going to do it this way. So I'm going to create a new structure, and I'm going to create, we'll call it input data. So we're going to create a struct. Again, this is a structure of input data. But instead of this being a component data, this is going to be a buffer element data. And a buffer element data, it works like a component, but instead of it being a one component attached to an entity, a buffer element data basically can be an array of these data elements attached to an entity. So I can have 10 or 64 or 1,000 input data instances attached to a single entity, and then I can use all that data in a system. And that the reason I'm doing this instead of it being just a component and being the inputs that have been assigned is I want to buffer up our inputs. I want to basically gather inputs in one system and just let it do that. And then we'll build another system that's going to apply those inputs. And by doing this system, what it does is it gives us a stream of inputs that we can decide later on. I want to do something else with this input data in a different system if I want, or don't want. It's up to you. But I want to do this as an input system. So in a Space Invaders game, there's really only a couple of like input flags I care about. I'm going to keep it simple. We're going to say bool left, is left down, is right down, or is the fire button down, right? Should I move left or should I move right or should I fire? And it can be a combination of any of these. That's all this is from a structure perspective. We're not defaulting. There's no functionality in here. This is just a component, or it's a component like data. It's a buffer. I also need to give it an internal buffer capacity. This is telling the entity component system by default, whatever entity has this data element, I want to initialize 64 of them and just maintain that as a kind of capacity buffer. You can make this as large or small as you want. There is a cap. We're not going to go into the details on what that cap is. In general, though, keep this small if you can. I'm going to say I want to be able to buffer up to 64 of these input data items. It'll make sense when we write the system here in a second. So to add this component, if you notice we had this player tag and I had this generate authoring component as an attribute. Normally, you cannot add a generate authoring component or tag to a buffer element data. But we need a way at the conversion system to say is when I create the player entity, not only do I want to add a player tag, but I also want to make sure that entity has this input data to it. And you can't do that by default by using the authoring component attribute. Instead, we have to go write our own kind of convert mono behavior. So we're going to do that. And we're going to call this the player authoring behavior. So when this opens up, it's going to be a mono behavior, which is okay. But as well as it being a mono behavior, we need to make sure that it can implement the iConvert game object to entity. This is a new interface that's part of the entity system up here. And what this does is, let's go ahead and implement the missing members. It'll give us one. It just gives us this convert method, and we need to implement it. And this is a pretty simple system. What this allows you to do is you can now attach this mono behavior to any game object that's going to be converted to an entity. And then this lets you hook into the conversion system and do whatever you want. You can add multiple components. You can add buffer elements here, which is what we're going to do. You can go nuts here if you want. You can create more entities. So that one spawned entity from the conversion system can create a bunch of child entities if you want. This kind of gives you full control over what the conversion is going to do, and then you can write code to kind of do custom conversions, which is what we're going to do right now. But this is a very simple thing we need to do. It's just because the editor doesn't have really good support for buffers at the moment. So instead, what we're going to say is from this entity manager, which is how we modify, control, and manipulate entities, I want to add a buffer, which is our input data, and I want to add it to our entity. So what I'm saying is, hey, entity manager, take this input data buffer element and add it to this entity. And we know this entity is going to be the player because I'm going to go add this mono behavior to our player game object. So that at conversion time, that convert's going to run and it'll add what we want. So let's go add the two new things we did. We have this player authoring behavior, and it doesn't have any input data. You can add input data here. You can add properties that you can then use at conversion time if you want. And we're going to also add our player tag. And our player tag also has no data either. Remember, this was an empty component. So now we have this player authoring behavior, and we have this player tag behavior. And that's it. That's all we have from this player. If we were to hit play right now, and look at this from the entity debugger, and we look at all entities, if we look at player, you'll see that we have some new data. We have this input data. It's empty. There's no buffer elements. It has capacity, but it doesn't have any instances. And then it has our player tag, again, which doesn't have any data. It's just used as an empty component for a tagging system that we'll start using in a moment here. So how about we go implement this in our input system? And it's going to be two systems because I want to show you guys that you don't have to do everything in these large monolithic systems. You can have very finite very focused, solid principle-based systems in an entity component. And by doing that, I think you will find that your game logic is going to improve. You can start to reuse systems for other items, for other entities in your world. They don't have to be highly specialized for a player or an alien or a mothership. We don't need those three mono behaviors. Now we can share a system and we can share components for aspects of those. Like if we want to move a mothership or an alien or a player, we don't need independent systems for all those. If we didn't want to, we can have one system that's just a mover system. And then that's just looking for entities that have a speed component. And then, it's just doing the movement. And it can handle it. Basically, that means anything in the world now, as long as you add a speed component to it, it will get moved by the mover system. That's kind of one of the major powers of an enemy component system. It's highly decoupled. You don't have to model an object using a class. You model an object using a series of components. So this actually will be a class. This is not a structure because this is our first system. And we're going to make this a very simple system. And to make a system in the ECS, you can inherit from a few different items, a few different base systems. There is the system base. I suggest you kind of steer clear of this. This is a very low level. You do a lot on your own. What we're going to use today is a component system. This is the highest level system you can implement that kind of wraps a lot of the ECS for you and makes it very simple to implement. And to use this, there is a member you need to implement, which is this protected override void on update. On update is going to get called whenever this system is executed. That's important that I say it that way instead of saying every frame. It is not guaranteed that a component system or an ECS system is going to get called every frame. It depends on a lot of factors. So that's why this is not just like a mono behavior update, which absolutely gets called every game frame. A component system or a system in an ECS does not necessarily get called every frame. And in fact, sometimes it can even be called multiple times per frame. Depending on how your systems are implemented and your groups are implemented and what's going on there, it can be called from 0 to many times in one frame. So it's a departure from the frame system. It's a very simple concept, obviously. It's its own update loop. It will get updated in the update time frame. So all mono behavior updates happen first, and then the systems run, and then those systems could execute. They might not execute, or they might execute multiple times, depending on many factors. In general, for a component system, it will get executed once per game frame or once per game update loop. So in general, it does happen once per frame, but that's not a guarantee. We are going to need a private member here. So I'm going to start talking about entity queries. And entity queries are kind of at the heart of an entity component system. Because when we start talking about entities and components that get attached to an entity, and then the systems that execute logic over entities that have components, in order for all of that work, you basically are doing queries. So that's what when we start building up objects now, so I have a player entity. And what is a player entity? All a player entity is an entity that has the player tag and that has this input data. If any entity, and there could be more, has player tag and input data, to our view of a system, that's a player. So if you're doing a multiplayer game, that might be how you have multiple players. You just have multiple entities, and they all have player tags, and they all have this input data, and they can execute off of that. So that's what makes an object in an ECS system. It's not the entity itself, because remember, that's just a thing. It's just an ID. It's the components that get attached to that entity now make up an object, and that's how functionality gets built up. So when you think about an entity, think about the components that are attached to that entity, and that's what kind of entity it becomes. So we have this player query, and in an ECS system, it's all about querying. It's all about just finding these entities that meet these query requirements, aka components that are attached to them. So to build this query, we need to override one more function, and it's going to be the onCreate. OnCreate gets called one time when the system is instantiated. There's also an onDestroy if you need to do any cleanup. It's very similar to start and destroy in a mono behavior. So this is not per entity. This is not on the creation of an entity. This is the on creation of our input gather system, which will only exist one time in the world. All systems are singletons. You're not going to have a system running multiple times, or instances of a system running multiple times in the same world. It's a singleton. We need to build this query now. So player query. So I said we're using this component system as our base class because it gives us a lot of really nice functionality, which is this function get entity query. And then we can pass it what component types or what kind of components are we going to search for. So we want to say I want a component type. And then I want that component to be a read-only component. And we can then use generics here that say player tag. And that's all we're doing. I want to query the entity manager. Under the hood, that's what it's doing. It's using that entity manager. I want to query the entity manager and go find me all entities that have attached to it a component of type player tag. And then we're also giving this query a hint that says, we're only going to use this data as a read-only. I'm not going to try and write this data back to the component and to the entity. It can optimize itself a little better here on how it lays the data out. Just know that if you're going to use the data, if you're going to use the components in here and you're going to write to it, this should be read-write. We'll see that a little later. But since I know that I'm only using this to find a player by its tag, I want this as a read-only component. So this creates a query. This does not execute the query. This is basically building the query. If you've ever used SQL before, this is building the statement. We are not executing the statement just yet. So in onUpdate is where we want to execute that statement. So what I want to do is I want to go get the entity. So let's go get the player entity. We can now execute this query by saying get Singleton Entity. This is a shortcut. I know for a fact that this is a single player game, and I know for a fact, because I'm developing it, that we will only ever have one entity that has a player tag. And because I know that to be a true statement, I can use this shortcut called get Singleton Entity, which will, from a query standpoint, go get me the only entity that should exist. If there happens to be 0 or more than 1, if the count is not 1, this will throw an error. It doesn't just return the first one it finds. This will throw an error because you're telling it there should only be a singleton. There should only be a single entity in the entire world that meets this query. And if it doesn't, then you're going to get an error. But I know that this will always be 1 because that's how we're designing it. I can use this nice shortcut. It's a way to use singleton entities. We're going to use a bunch of them today because singleton entities are there's nothing wrong with them. It's a way to store global data that you can then use through a bunch of systems. But in this case, I just happen to know that it's a single player game, so I can kind of use this shortcut. Now that I have the entity, I need to go get that input data that we talked about or that we designed. And that basically is this buffer, and it's kind of it's a dynamic buffer. And what a dynamic buffer is, think of it as a list or an array, and it's the size of it can grow or shrink as need be. Its capacity can increase without having to reinitialize the underlying array. Well, under the hood, that of course is what's happening. And again, since we're using a component system, I can use a lot of nice shortcuts off of the base class here, like this get buffer from entity. And I want to say input data and the player entity. Oops. And this is basically going to, if I could type, there's our input buffer. Sorry. One thing I gotta fix. So what does this do? Get buffer from entity. This is going to return an array. This unfortunately, you can't just pass in the entity that you want to get the buffer for. What this does is it actually returns an array of input data dynamic buffers, and the indexer, how you access into that array, is you pass it an entity. So that's why we're indexing into the array using our player entity, and then that will return us the input buffer that exists on the entity. This is, I know I'm doing this as a little complex. We're going to get past it here in a moment, and then we'll get to a very standardized ECS stuff. But it's important to understand how buffers work, because you're probably going to be using them in some form or fashion when you're doing some game development using ECS systems. So it's very important to understand how these work. So what do I want to do now? We have our buffer, and this is an input gather system. We're not executing our input here. I just want to gather our input and store it in this buffer. We're going to go write another system that executes off that input. So to gather the input, we need to create a new input data. I'm going to call this input, and I'm going to assign it to default for the moment. And then now we can actually check, since this is Unity, we can still use Unity things like get key. And I'm going to hard code left arrow. Obviously, you can use the input system here to know what left is and what right is and what the fire is. We're keeping this very simple today. I want to say input left is true. And then we'll do some other checks, right? If inputs get key code right arrow, input right equals true. If input get key code space. So if you hit the space bar, we will input fire. True. So we are now creating a new input data object. This basically gives us a new structure of input data. I'm assigning the values depending on what the current key states are. Remember, this is not necessarily latest data. This is a snapshot of data on this frame, like when this was gathered. This is our snapshot of data. And I have that snapshot of data, and I just want to add it into our dynamic buffer. And that is it. This is all we need to do for this input gather system. This is straightforward. This is a very, very simple. We're just gathering input. So we're taking in all the input data, we're gathering it, and we're putting it into this dynamic buffer. Now, why am I doing it this way? Because I could say if input key left arrow down, I could then implement the logic move player left, right? We could implement that logic here. We could just move the player left. You could do that. I would not do that, because now you're kind of breaking this loose coupling of what an ECS system is. You want to keep your systems as isolated and as finite as you possibly can. We're just trying to gather inputs. We're going to go write another system that will do some applying of these inputs, which is where we'll go move the player if the left arrow down. But not if left arrow down, but if our input.left is down. If input.left is true, we'll move left. If input.right is true, instead we'll move right. If input.fire is true, we'll attempt to fire a rocket. But we're keeping this simple. And this is a component system, and this is it. This is all we are doing. And if we were to go back into the game here and hit play, let's see if this works. So we have our player, and now you can see that we're actually building up all this input data. And if we're not careful, we will overflow. But we are building up all this input data. Right here, we have these 4 elements here left, and they're all false. And that's because every frame, I'm adding a new input into the input data, and we're not processing any of it. And that's okay. But this data is getting set, but it's getting set to default values because the keys aren't down. I don't have left key down, or I don't have the left arrow down, or the right arrow down, or I don't have space down, or anything like that. And it's going to keep building this up, so we got to be careful. But that's okay, right? This is doing what we want it to do. This system is running, and it's starting to gather inputs for us. Essentially, now what we want to do is we want to apply our inputs. So let's create a new class, which is going to be a new system. Apply inputs system. And this, again, is going to be a component system. We're going to be using this over and over today, guys, so get used to this component system. This is how we build components in our game. And we don't need a query here. I'm going to show you the alternative means of doing queries, the more built-in, the kind of the easier way that Unity wants you to do queries. Now, you can still do queries like we did on this input gather system. There's nothing wrong with doing what I did here. But there are other ways to do it, and I'm going to show you those right now. So what we can do, since I'm implementing component system, there is this entities off of component system, and we're inheriting from it, so we have access to it. And from there, we can then call this for each method. And this for each method allows us to pass in a lambda or an anonymous function or a function signature, whatever works for you. We are going to give it an anonymous function or a lambda. It's kind of the normal process. I want a query for entities, if I can type this correctly. I want to find entities that have a dynamic buffer of input data. Let's make sure that gets referenced. I want to have a ref to our translation. We talked about this at the beginning. This is a component part of our transformation. When a entity is converted, when a game object is converted into a entity, it gets translation, rotation, scale, and local to world. Translation essentially is the local position before it's rotated and scaled. So we want to get the current position because we're going to go update it. And then I also want to get our, well, we don't have speed data yet, so we will have to go write that in a moment, and that's okay. But this is the beginnings of a query for us. So I showed you how we wrote a query before using component types, and you can create an entity query. This is going to do that behind the scenes. So what is this going to do? This is going to go find all entities that have the input data component and a translation component, and then iterate over them. It's going to execute this method for each one of those that exist. So let's also add a item to the query that I just want to be part of the query, but I don't want it to be part of the data. With all player tag. So by adding this with all player tag before the for each, it's going to say, okay, now go find me all entities that have input data, that have translation, and also have player tag as components. So this is essentially, this is how we build objects. So again, instead of creating a player class and then adding all our logic to a player class, we have these series of components, and the combination of those components is what creates an object. We have an entity, and this entity has input data. It has a player tag, and it has a translation. If you have those components in our world, that means you're a player object. And then I want to have access to the input data and the positional data of the components. I want access to that data. Player tag has no data. So from an optimization standpoint, we just want to say with all. I just want to add it to the query, but I don't want it as part of my data whenever it gets called. And then we could do whatever we want here with this information. So since I have this as a buffer, this is an array, and this could be more than one element, because maybe our input gather system ran several times before our apply inputs system ran. I want to iterate through each one of those. So just like a normal array, we can go through this input buffer length. So we'll just have a little for each here. Let's go grab the input data off of that buffer. And then this is where we can apply logic, right? So if input dot left if input dot right, if input.fire. We can decide what we want to do when these three states are selected. Fire a rocket. We will do that later, but I want to implement these inputs. So if left is down, right? If on this frame we have an input data of left, I want to move the player one space to the left. Essentially, for this frame, I want to move left. So what's it take to move? Well, for us to move, we need to know how fast we should move so that we can say, I want to update. You could hard code something here, right? We could say our position value is minus equal since we're moving left, right? Left, we go lower X, right, we go higher X. We could hard code it. This would work. Let's see what happens if we do that. And if I want to do right, we basically add 1 on here. So position minus equal 1, position plus equal 1. Let's go see what happens when this runs. The other thing I need to do before we get into that, after I've iterated through all of our input buffer, I've now executed on this whole input buffer. I want to make sure we clear this out. And if we don't clear the input buffer out, what's going to happen is next frame, we're just going to run through that same input buffer again. And we'll quickly move right infinitely off the world. So we need to make sure that once I've processed through the whole input buffer, let's make sure we clear the input buffer. And the next frame, we can gather some more inputs and we can apply them. Now, the other thing we can think about from a system standpoint is the order that systems run in. I have a gather system and I have an apply system. That would normally mean we want the input system to run first, and then we want the apply inputs to run after that. By default, that's not going to necessarily happen. The order that these systems run is when they're registered, and there's no guarantee on when that happens unless you tell ECS how you want it to work. So we can say that we know this should run after a specific system, so we can add an attribute that says update after a type of our input gather system. So we know that we are going to run this after we've gathered input. So now input gather will run first. This will run after that. We can also be very safe here and say we want to make sure this also runs before our transform system group. This is going to happen normally for you anyway because the system's added to the simulation group, which always runs before the transform system group. But if you want to be explicitly clear, we want to say that the apply inputs should be happening before the transformation system group executes. And that's because we want to make sure that our inputs are updating our position so that when the transform happens, it gets applied in the same frame. And if you don't do this, there could be a possibility that we're going to apply inputs after we've transformed, and then we're going to be a frame behind, and it could look a little weird. So this is just a safety precaution, but by default, normally this is going to be a guarantee, only because systems, unless you say otherwise, go into the simulation system group, and the transform system group runs after simulation. But we just want to be explicit here. So what happens if we go run this now? Let's adjust a little here. Let's go see what happens when this runs. So we have player, and you notice how player doesn't have any input data anymore? Well, that's because we're applying our systems. So if we look at our game, we have this input gather system in our list here. And if you notice here that it's running afterwards is the apply input system. So we know the ordering is correct now. We have input gather. We have apply inputs. Everything is working in the right order. If we click on this system from the debugger here, which is a really nice debugger, it's pretty good, we can see what's happening. Here's a query that's happening. We're trying to query for any entities that have the player tag. When it's in white, you can see if we click on some other things, there's going to be some different data. This is an RW for read write. But if it's in white, it's a tag. We know that we're just querying for this data as a read only, essentially. and we don't actually not even read only. We're querying this as a query only. We don't want to access the data. And our input gather system is running, and it's taking 0.02 milliseconds, and it's only running over a single player because remember, it's a singleton. So here's our player. And this is going to gather those inputs. But immediately after that, in the same frame, we are then applying the inputs. And here is another query that's happening that says, I want to read write input data. This is essentially how many entities meet this query, right? That have input data, translation, and the player tag. There's only one, it's our player. And then we're applying those entities, or applying that input data, and then we're clearing the buffer. So that's why this input data is always empty. But if I was to hold down the left key, so let's take a look at this translation data down here. We have translation data, and we have local to world data. I'm going to hit the left key, and you can see that instantly all of our data starts to change because we're applying that system. Right now, we're making change in the system. We're taking these components that are attached to an entity, and we're applying logic to them in this apply input system, and we're able to start changing data. And if I hold right, we go that way, and data changes. Obviously, we're not rendering anything right now. So let's go fix that. Why don't we go fix that? So we have this player as a game object. Why don't we add a 3D child object of a quad and call this GFX for graphics? And this is a quad right now. So if we just hit play real quick, and then I hit the left key, boop, you can see that, instantly we flew off into space somewhere. And why is that? Well, if you noticed when I took this positional value and I minus equal 1, this value is a float 3. So not only did I subtract 1 off the x, but we actually subtracted 1 off of all 3 of our axes. And then so that means we moved to the left 1 and we moved down 1, and not what we wanted to do, right? Instead, what we actually just want to do is say .x. Because we're a Space Invaders game, we're in a 2D plane and we only can move back and forward or left and right. We can't move up or down. We can't move closer to the camera or away from the camera. So if we fix that real quick and we hit play, and then we try and hit left here in a moment, you can see that we can now start moving this little box left and right. And it moves really fast. It's actually hard to control. And the reason that is because we're multiplying by every frame by 1. And if you've done any type of Unity development before, you know that typically in an update frame, you should never multiply by a fixed number like this, because you don't know every frame we're going to update by 1. But now our movement is frame dependent. If we were running at 30 frames a second, we would be moving at 30 units per second. If our frame rate was 200 frames a second, we would now move at 300 units per second, right? So our movement here is frame dependent, and that's not good. And not only is it frame dependent, but it's actually system update dependent, because if our system runs multiple times in a single frame, we might actually move more than 60 frames a second. We might, if we're executing 2 times per frame, we're going to actually be 120 movements per second, and that's not good. So to solve that, just like in a mono behavior, there is delta time. So we'll say float dt is equal to this dot time dot delta time. You don't want to use, there is Unity engine, right? Time, delta time. No. Do not use this in a system, in an ECS system. Do not use Unity engine time, delta time. This is a bad thing to use. This is the delta time for the frame. And remember, a system could potentially run more than 1 time in a frame, or it might run less than 1 time in a frame. So you want to use the system's delta time, which will be accurate for how often it's running relative to the frame rate. So you want to use this time. And the reason why we store this outside the entities, guys, if you were to try and say, take delta time, and if we take our speed, which is 1, and we just multiply it times delta time, the compiler, Visual Studio, whatever compiler you're using, will not complain. This is valid software. This is valid code. But if we were to look here and try and run this, we should get an error. I guess we will not get an error. We'll get an error later on. You should never do this. Try not to ever do this. Don't access properties off of our instance. So this.time, we're accessing a field or a property from our base class. Don't do this within this for each loop of an entity component of a system of an ECS. Instead, cache it outside of the lambda, like I do here, and then just use that throughout. And it'll make sense in a bit when we move into the job system and the burst compiler. That becomes a compile error in the Unity side. Unity from a burst compiler does not allow you to use properties or fields that are instanced or they're instantiated. So instead, you want to cache it. Just cache this data outside of your Lambda. And then you can use this as a local variable inside of here. And it also, what it does is it tells the compiler that, hey, I am using this as read-only data because a float is a copy of delta time. It's saying that I'm using this as a read-only data because in here, technically, you could say this, right? dt equals, you could override what delta time is. And we're saying that if you do that, it's not going to update the true delta time. So it's telling the compiler that we're using this essentially as a read-only instantiation or a copy of the real delta time. So you always want to do that. And if we come back to the game now and we hit play, instead of us jumping around very far, we now have a speed, right? So if I hit left, we move a lot slower. Because now we're not moving 1 unit per frame. We're moving 1 unit times the delta time of that frame. So we'll get a smooth animation or smooth movement no matter what our frame rate is. So remember, again, we're using our input gather system as a recap. We are gathering input first. So if left is down, we're basically setting a flag on our input that left is down, or that we should move left, or we should move right, or we should fire. Essentially, what's the key state at that time? And then when we apply those movements, we're saying that if we are holding left down, just move our position to the left by a speed. If right is down, move our position to the right by the same speed. And then obviously, if the fire button is down, we will fire a rocket in a little while. But essentially, that's all we're doing from this apply inputs. The one problem we have here is the speed. Right now, this is hard-coded into our system. You could do this. There's nothing technically wrong with having our hard-coded speed here. It does make it more difficult, obviously, from a design perspective to change the speed of the player. You have to go modify your code. So instead, why don't we just go add a component for speed data? So let's just call it speed data. So we'll get a new structure. Remember, components in the entity component system for Unity are all structs. They are structs, and it won't let you use a class. So I'm adding an iComponent data. We're adding the generate authoring component. We're going to be doing that a lot for most of our components. And then I'm going to add a public, has to be public, float value. Wait, what's our speed value, right? In what direction should we move data? And actually, let's create this as a float3 even. And we're going to have to import mathematics for that. So float3, don't use a vector3. A vector3 will not be allowed because a vector3 is a class. A vector, that's numeric, sorry. If we were to use this in Unity, right? A vector3, is a struct. But it's not a blittable struct. It's not usable in the ECS system. So you don't want to use Unity Engine. You don't want to use Vector3. You want to use the new Float3, the new Float2. There's Float4 if you want to use if you want a rect. But you want to use the new mathematics here, and it'll throw an error if you try to use a vector. So you'd be okay. It's not like you can use it and be in trouble. So make sure you're using the new systems. And we're just going to call it value here. And it's going to be a float3 for speed. So let's go back to our apply input system. And instead of us applying this 1f to the x, instead we can now minus equal speed data, which we need to go reference data speed. So now we're saying, let's modify our query. Let's go find all entities that have a player tag, input data, position, and speed. That's what makes up a player now. If a player doesn't have speed data, they're not a player. And once we have that data, we can use its value and we can get rid of this X aspect and just apply our speed times time, right? Times our delta time, which you've seen all over the place from a Unity perspective. Now, we're going to subtract that speed if we're moving left, and we're going to add that speed if we're moving right. So now that we've updated our system here, if I were to play the game, which we're going to do here in a moment, and I hit play, and we try and move right or left once it starts, you're going to see that we're not moving anymore. And why are we not moving anymore? Well, let's go look at our input gather system. We have a player. We are actually building up a lot of input data, so we're not clearing out our input data. And if we look at our apply input system, it says it's not run. And when we look at our query here, we have no items in our query. And why is that? Well, we're now querying for speed data. We now expect a player to have all of these components, which is this new speed data as well, but we have not gone and updated our player to have that speed data. And then now that we have speed data, in the editor, just like a mono behavior on a game object, we can actually set the defaults for that. We can actually change the values. We can only do it at design time. At runtime, you don't have access to this data to edit in the entity system at the moment. So this is where our value is. So let's give it a speed, and we only want to move on left and right, so on the X system. So what value do you think we should use here? I'm going to say let's move at 10. So 10 units on every input command. And we'll hit play here. And now as we move, we actually move a lot faster, right? Obviously, we're not moving at 1, we're moving at 10. And I like this speed. Now, here's the thing, though. This is a Space Invaders game, and you should not be able to move off screen. But look at this. We can move off screen because we have no logic in here that says, hey, what's the maximum place I can move? Like, what's my screen position that we should be moving to? Or what's the bounds of the game? And that's not implemented, and maybe we need to go implement that. So remember as a recap for all of this, we are converting a game object into an entity, and by default, Unity's conversion system converts our transform mono behavior into 3 components or 4 components. It gives us a position component. It gives us a rotation component, right? Position, rotation, scale. Those are 3 separate components. And then it has this local to world component, which is basically the matrix of position, rotation, and scale in the world. So that's the final render position, essentially. The Unity also gives us that system behind the scenes that takes all of those and builds the matrix every frame for us or every update. And calculates where it should render. And then the render mesh system, which is part of that hybrid package, renders the mesh, which right now is just a quad with the default material, wherever that world position is. And what we're doing in our apply input system is just taking that positional data, right? We're taking our translation component that entity gives us, that Unity gives us for the entity, and we are just modifying that position. So this is in a classic mono behavior. In an update, you would take the transformation or the transform, and then you would take the position off of it, and you could adjust the position axes, right? You can take transform.position.x, and you can move it left or right. And then the system would render that in world space wherever you adjust that. This is that same concept in an entity component system. But we don't have a world bound. So when we play that, but before we get to world bounds, why don't we update our mesh here? So we have a material, and it's using a default material. In our default project, I've actually already pre-built a bunch of materials. So let's see, we have a player material. Let's just go drag it onto here, and we'll actually get a, instead of a gray box, we can actually get a graphic on here. Because, graphics are cool. And we can also, let's adjust over here. Let's, boop. Let's actually go into 2D mode because we are making a 2D game essentially, even though it's not an orthogonic camera. And let's adjust our position of where we are. Let's just move them down. So this is the start position that I want. And now if we play again, because I've updated the transformation position, right, -5, what's going to happen in the entity world, if we look at our player, we're going to get a translation defaulted to -5, and then that gets translated when he goes to the matrix into the local to world of also -5. And now as we move left and right, we'll start adjusting the X position. Our Y position obviously never changes. That axis is fixed because we're not adjusting it from our speed data. Here's our speed data right here, which we're applying 10. And that's essentially how that works. So now we have a little graphic here, and it's better than a gray box.